Welcome! Today, we'll be exploring an exciting problem from LeetCode, number 1552, magnetic force between two balls. This problem challenges us to think critically about placing objects with constraints, and we'll discover some interesting approaches to solve it. Let's dive in. In this problem, you are given an array called position, where each element represents the location of a basket on a line. For example, if position I equals 5, it means there is a basket at position 5. You are also given an integer m, which specifies the number of balls you need to place into these baskets. The goal is to place these balls in such a way that the smallest magnetic force between any two balls is as large as possible. Now, the magnetic force between two balls placed at positions x and y is defined as the absolute difference of their positions, that is, x, y. Your task is to compute and return the maximum possible value of this minimum magnetic force by placing the balls optimally. For example, if there are 5 baskets, you need to determine how to distribute the balls in those baskets to maximize the smallest distance between any two balls. The constraints ensure that the problem stays computationally feasible even for large input sizes, and the output will be a single integer, which is the maximum minimum magnetic force achievable. Let's look at an example to better understand the problem. Suppose the input is position equals 1, 2, 3, 4, 7, and m equals 3. This means we have baskets at positions 1, 2, 3, 4, and 7, and we need to place 3 balls into these baskets. One way to distribute the balls is by placing them at positions 1, 4, and 7. The magnetic force between balls at positions 1 and 4 is a 4, 1 equals 3, and the force between balls at positions 4 and 7 is also a 7, 4 equals 3. The minimum magnetic force in this configuration is 3, and it turns out that this is the largest possible minimum force you can achieve with 3 balls. Therefore, the output for this example is 3. This demonstrates how the placement of balls directly impacts the magnetic force between them, and our goal is to maximize this minimum force. In another example, suppose the input is position equals 5, 4, 3, 2, 1, 1 billion, and m equals 2. Here, there are 6 baskets, and we need to place 2 balls. The optimal placement is to put one ball at position 1 and the other at position 1 billion, which is the farthest possible distance between any two baskets. The magnetic force in this case is 1000000000001 equals 999999999. Since we only need to place 2 balls, this is the maximum possible minimum magnetic force. Therefore, the output is 999999999. Notice how the constraints of the problem, such as the large range of the position array, require careful consideration to ensure the solution remains efficient while achieving the desired result. Now, let's discuss some edge cases that you might encounter. For the smallest input, consider position equals 1, 2, and m equals 2. Here, there are exactly 2 balls in 2 positions, so the only possible placement is to place 1 ball in each basket. The magnetic force between them is 2, 1 equals 1, making the output 1. On the other hand, for the largest input, imagine position contains 100,000 elements, with values spread across the range up to 1 billion. In such cases, the algorithm must be efficient to handle the massive data size. Another edge case involves unsorted input. For instance, if position equals 3, 1, 4, 2, and m equals 2, you must first sort the array before calculating the magnetic force. Finally, consider a scenario with closely clustered positions, such as position equals 1, 2, 3, 4, 5, and m equals 3. Here, the optimal placement requires careful calculation to maximize the minimum magnetic force, even when the positions are close together. The key to solving this problem lies in using a binary search approach to determine the largest minimum magnetic force. First, you sort the position array to ensure the positions are in ascending order. Next, you perform a binary search on the possible values of the magnetic force. You start with a lower bound of 1 and an upper bound equal to the difference between the smallest and largest positions in the array. For each midpoint value of the magnetic force, you use a greedy algorithm to check if it is feasible to place all the balls such that the minimum distance between any two balls is at least mid. If it is possible, you increase the lower bound to try larger values of the magnetic force. If it's not possible, you decrease the upper bound. This iterative process continues until you find the maximum feasible value of the minimum magnetic force. To illustrate the approach, let's revisit the first example with position equals 1, 2, 3, 4, 7, and m equals 3. After sorting the positions, we perform binary search on the magnetic force. Suppose we try a midpoint value of 3. Using a greedy approach, we place the first ball at position 1, the second ball at position 4, and the third ball at position 7. The distances between the placements are both 3, which satisfies the condition. Since this works, we continue searching for larger values of mid. Eventually, we determine that 3 is the maximum possible minimum force. In the second example with position equals 5, 4, 3, 2, 1, 1 billion, and m equals 2, we start with a sorted array and try values of mid, such as 499,999,999. Placing one ball at position 1 and the other at position 1 billion satisfies the condition. By increasing mid, we find that the maximum minimum magnetic force is 999,999,999. This binary search approach ensures we efficiently solve the problem, even for large inputs. When tackling this problem, one intuitive approach is the brute force method. Here, the idea is to try all possible configurations of placing m balls into the baskets to find the one that maximizes the minimum magnetic force between any two balls. This involves generating every combination of m baskets from the position array, then calculating the minimum distance between any two balls for each combination. Once we have these distances, we simply return the largest value. While this method is straightforward and easy to implement, it becomes computationally expensive as the number of baskets increases. The time complexity grows exponentially because the number of combinations is proportional to n(m), where n is the number of baskets. This makes the approach infeasible for larger inputs, like when n goes up to 100,000. Despite its simplicity, the brute force solution highlights the need for a more efficient strategy to handle larger constraints effectively. A more efficient solution is to use the binary search approach. Instead of trying all combinations explicitly, we leverage the properties of the sorted position array to systematically narrow down the search for the maximum possible minimum magnetic force. The key idea here is to treat the problem as a decision problem. Can we place m balls such that the minimum magnetic force is at least a given value, mid? To do this, we first sort the position array, which allows us to define the search space for the magnetic force. The smallest possible force is 1, representing the smallest gap between adjacent baskets, and the largest possible is the difference between the first and last elements in the sorted array. Using binary search, we iteratively test a candidate force, mid, and use a greedy approach to check its feasibility. If placing the balls with at least mid distance is possible, we search for a larger force; if not, we explore smaller values. This systematic pruning of the search space makes the method highly efficient. The binary search approach is not only intuitive but also computationally efficient. Sorting the position array takes O, n log n, time, and the binary search itself involves O, log, max_distance, iterations, where max_distance is the difference between the first and last positions in the sorted array. For each iteration, we perform a linear scan of the baskets to check the feasibility of placing the balls, which takes O, n, time. Combining these, the overall complexity becomes O, n log n, which is scalable even for large inputs. This efficiency is a significant advantage over the brute force method. However, the trade-off lies in the feasibility check, which requires careful implementation to ensure correctness. By leveraging the sorted array and binary search, we minimize unnecessary computations, making this approach both practical and robust. Given the constraints and the need for scalability, the binary search approach is the clear choice for solving this problem. While brute force provides a simple baseline, its exponential complexity makes it impractical for larger test cases. The strength of the binary search strategy lies in its ability to systematically narrow down the possible values for the optimal magnetic force, reducing the problem to a series of efficient checks. The key insight, or aha moment, comes from reframing the problem as a decision problem, which transforms a combinatorial challenge into one that can be solved in logarithmic iterations. Although implementing the feasibility check adds some complexity, the performance gains far outweigh this trade-off. Ultimately, the binary search approach strikes the perfect balance between efficiency and feasibility, making it the ideal solution for this problem. The goal of this problem is to maximize the minimum magnetic force between M balls placed in a given set of basket positions. To break this down, let's start by defining magnetic force, which is the absolute difference between two positions, x, y. The task is to strategically choose M positions from a sorted array of N basket positions to ensure that the smallest magnetic force between any two balls is as large as possible. Since the positions are sorted in ascending order, we know that the greater the distance between two balls, the greater the magnetic force. Therefore, we aim to maximize this minimum distance. A simple brute force method involves generating all possible combinations of M positions from the N baskets, calculating the minimum force for each combination, and returning the maximum value. However, this is computationally expensive, and we need a more efficient approach for larger inputs. To solve this problem efficiently, we can optimize the process using binary search. First, we ensure that the basket positions are sorted, which simplifies calculations and ensures we can focus on distances without worrying about order. Then, we define the search space for the minimum magnetic force. The smallest possible magnetic force is 1, which is the smallest difference between any two distinct positions. The largest possible magnetic force is the difference between the first and last positions in the sorted array, positions n1, positions 0. Using binary search, we test different candidate values for the minimum magnetic force. For each candidate mid, we check if it's feasible to place M balls such that the minimum magnetic force between any two balls is at least mid. If it's feasible, we try for a larger force by adjusting the lower bound of our search space. If it's not feasible, we reduce the upper bound to test smaller forces. Feasibility checking is key to making binary search work in this problem. To do this, we use a greedy algorithm to verify if placing M balls with at least mid-magnetic force is possible. Starting with the first ball placed in the first basket, we iteratively place each subsequent ball in the farthest position that maintains at least mid-distance from the last placed ball. If we successfully place all M balls this way, the candidate mid-value is feasible. Otherwise, it isn't. Once we identify the largest feasible mid-value, this becomes our solution, as it represents the maximum minimum magnetic force. The core insight is that binary search allows us to efficiently narrow down the range of possible forces, while the greedy approach ensures that we can quickly check feasibility within each binary search iteration. Let's analyze the computational complexity of this approach. Sorting the positions takes n log n, which is a one-time cost. The binary search operates over a range defined by the maximum possible magnetic force, which depends on the difference between the first and last positions. This contributes log max_distance iterations. For each binary search step, the feasibility check runs in n, as we only make a single pass through the positions. Combining these, the total time complexity is n log n plus n log max_distance. We also need to handle edge cases, such as having only one ball or position, large gaps between positions, dense clusters of positions, or cases where placing M balls is impossible. The pseudocode provided summarizes the entire algorithm, including sorting, binary search, and the greedy feasibility check. The final implementation of the algorithm returns the result after completing the binary search. The helper function, can_place_balls, performs the greedy feasibility check. It starts by placing the first ball at the first position and iterates through the array to place additional balls, ensuring each new ball is placed at a position that maintains at least min_force distance from the last placed ball. The function returns true if all M balls are successfully placed and false otherwise. This helper function ensures that we can efficiently test each candidate magnetic force during the binary search. By combining the binary search framework with this greedy feasibility check, we achieve an optimal and efficient solution to the problem, balancing the need for maximizing the magnetic force with the placement constraints of M balls. This code implements a binary search solution to maximize the minimum magnetic force between M balls placed in a sorted list of basket positions. Here's the explanation. 1. Sorting the positions. The first step is to sort the position array. This ensures that the basket positions are in ascending order, which simplifies the placement of balls. 2. Binary search setup. We define a binary search range. The smallest possible force, left, is 1, minimum distance between adjacent positions, and the largest possible force, right, is the difference between the first and last positions. the variable best_force will store the maximum valid force found. 3. Helper function, can place balls. This function checks if it is possible to place m balls such that the minimum distance between any two balls is at least min_force. Starting from the first basket, it iteratively places balls in the next position that satisfies the distance condition. If all m balls can be placed, it returns true, otherwise, false. For binary search logic, inside the binary search loop, the midpoint mid represents the current candidate for the minimum force. If can place balls, mid, returns true, it means this force is feasible, and we attempt to find a larger force by moving the left boundary to mid +1. Otherwise, we reduce the search space by moving the right boundary to mid 1. 5. Return the maximum force. Once the binary search completes, best_force contains the maximum magnetic force that can be achieved while placing the m balls. This approach is efficient, with a time complexity of n*log d, where n is the number of basket positions, and d is the range of possible forces. It ensures that the solution is both optimal and scalable for larger inputs. Here, we begin by importing the necessary classes and defining our solution class. The key method here is maxDistance, which calculates the maximum magnetic force between the balls. To start, we sort the position array to ensure the positions are in ascending order, which makes it easier to calculate distances between balls. Next, we define our search space for the magnetic force. The smallest possible force, left, is set to 1, and the largest possible force, right, is the difference between the maximum and minimum positions in the array. We also initialize a variable best force to store the maximum force we find. Then, we use a binary search approach. In each iteration, we calculate the midpoint of our search space, mid, and check if it's possible to place all m balls with at least this distance using the helper function canPlaceBalls. If it is possible, we update best force to mid and adjust our search space to look for a larger force. Otherwise, we narrow the search to look for a smaller force. Finally, once the binary search completes, best force contains the maximum magnetic force, and we return it. The helper method canPlaceBalls is crucial for determining if it's possible to place all m balls with a minimum distance of min force between them. We start by placing the first ball at the first position in the array, initializing count to 1 and lastPos to the position of the first ball. Then, we iterate through the rest of the positions. For each position, we check if the distance from the last placed ball is at least min force. If it is, we place another ball at this position, increment the count, and update lastPos to the current position. If at any point we have placed all m balls, we return true because the placement was successful. If the loop ends without placing all the balls, we return false, indicating that it's not possible to maintain the required minimum distance with the current min force. This method ensures that the binary search in maxDistance is able to accurately test different force values. In this problem, we aim to place m balls in n positions, which are provided as an array called position. The goal is to maximize the minimum magnetic force between any two balls. The magnetic force between two balls is calculated as the absolute difference between their positions, that is, x1, x2. For example, if the input positions are 1, 2, 8, 4, 9, and m is 3, the first step is to sort the positions array. After sorting, the positions become 1, 2, 4, 8, 9. Next, we define the bounds for binary search. The minimum possible force is 1, which is the smallest difference between consecutive positions, and the maximum possible force is 8, calculated as the difference between the largest and smallest positions, i.e., position, -1, position, 0. We initialize left as 1, right as 8, and best_force as 0 to keep track of the largest valid force we find during the process. We now perform a binary search to identify the maximum valid magnetic force. First, we calculate the midpoint of the current bounds, mid equals 1 plus 8, // 2 equals 4. The next step is to check if a force of 4 is valid. To do this, we start by placing the first ball at position 1. The next ball is placed at position 4 since the distance between them is at least 4. Then, we place the third ball at position 8, maintaining a distance of at least 4. Since all three balls are successfully placed, force 4 is valid. We update the bounds by setting left equals 5 and updating best_force to 4. We then calculate a new midpoint, mid equals 5 plus 8, // 2 equals 6. Checking if force 6 is valid, we place the first ball at position 1 and the second at position 8. However, we cannot place a third ball while maintaining a distance of at least 6. As a result, force 6 is invalid, so we update the bounds by setting right equals 5. With the updated bounds, we calculate a new midpoint, mid equals 5 plus 5, / 2 equals 5. To check if a force of 5 is valid, we place the first ball at position 1 and the second ball at position 8. However, we cannot place a third ball while maintaining a minimum distance of 5. Therefore, force 5 is invalid, and we update the bounds by setting right equals 4. At this point, the binary search loop concludes, and the largest valid force we found is 4. This value, stored in best_force, is our final answer for the first example. Now, let's consider another example with the input position equals 1, 3, 7, 9, and m equals 2. The first step is to sort the positions, which results in 1, 3, 7, 9. Then, we initialize the bounds for binary search. The minimum possible force is 1, and the maximum possible force is 8, so we set left equals 1, right equals 8, and best_force equals 0. The binary search process begins by calculating the midpoint, mid equals 1 plus 8, / 2 equals 4. To verify if a force of 4 is valid, we place the first ball at position 1 and the second ball at position 7, ensuring that the distance between them is at least 4. Since we successfully placed 2 balls, force 4 is valid. We update the bounds to left equals 5 and best_force to 4. Next, we calculate a new midpoint, mid equals 5 plus 8, / 2 equals 6. Checking if force 6 is valid, we place the first ball at position 1 and the second ball at position 7, maintaining a distance of at least 6. Since we successfully placed 2 balls, force 6 is valid. We update the bounds to left equals 7 and best_force to 6. Calculating another midpoint, mid equals 7 plus 8, / 2 equals 7, we verify if force 7 is valid. The first ball is placed at 1 and the second at 9, maintaining a distance of 7. This placement is successful, so force 7 is valid. We update the bounds to left equals 8 and best_force to 7. Finally, we compute the last midpoint, mid equals 8 plus 8, / 2 equals 8. To check if a force of 8 is valid, we place the first ball at position 1 and the second ball at position 9, ensuring a distance of 8. Since this placement is successful, force 8 is valid. We update the bounds to left equals 9 and best_force to 8. This concludes the binary search, and the largest valid force is 8. In a final example with positions 10, 20, 30, 40, 50, and m equals 4, following the same procedure yields a result of best_force equals 10 as the largest valid force. To analyze the time complexity, we start with the sorting step. Sorting the position array, which has a length of n, is performed using an efficient algorithm like timsort. This step has a complexity of O, n log n, making it the dominant operation during pre-processing. Next, we have the binary search loop, where we search for the maximum feasible minimum magnetic force within a range of values between 1 and position, -1, position, 0. With each iteration, the search range is halved, leading to O log d iterations, where d represents the difference between the maximum and minimum positions. Within each binary search iteration, we call the canPlaceBalls function, which checks if m balls can be placed at a minimum distance of min_force. This function requires iterating through the position array, taking O, n, time per call. Together, these components form the basis of our time complexity analysis. Now, combining the steps, the total time complexity of the algorithm can be expressed as O, n log n plus n log d. The O, n log n term arises from sorting the position array, while the O, n log d term comes from the binary search and feasibility checks performed in canPlaceBalls. Since d is at most position, -1, position, 0, the logarithmic factor remains relatively small. Therefore, the overall time complexity is determined primarily by the sorting and the binary search operations. Moving on to space complexity, the algorithm operates with constant extra space. The position array is sorted in place, and apart from a few variables used during computation, no additional memory is allocated. As a result, the space complexity is O1, excluding the input array, which makes the approach highly space efficient. Let's compare this optimized approach to a brute force alternative. A naive solution would involve iterating through all possible distances between 1 and position, -1, position, 0, to determine the maximum feasible minimum force. For each candidate distance, we would check placement feasibility by iterating through the position array, resulting in a time complexity of O(d*n). This is inefficient because d, the range of possible distances, can be very large. In contrast, the optimized approach reduces the number of candidate forces to check by leveraging binary search. This improvement reduces the time complexity to O, n log n plus n log d, which is significantly faster than the brute force method, particularly when handling large inputs where d is substantial. Finally, let's examine the best, average, and worst-case scenarios for this algorithm. In the best case, the binary search terminates early, and the canPlaceBalls function completes quickly. However, even in this situation, the sorting step still dominates, leading to an overall complexity of O, n log n. On average, all binary search iterations are performed, and the feasibility checks take linear time per iteration, resulting in a complexity of O, n log n plus n log d. The worst-case scenario is essentially the same as the average case, as the binary search and feasibility checks dominate the runtime. Mathematically, sorting the array contributes O, n log n, binary search involves O, log d, iterations, and each feasibility check takes O, n, combining to yield O, n log n plus n log d. Additionally, the space complexity remains constant at O, 1, as no extra memory is allocated beyond the input. This rigorous analysis confirms that the algorithm is both time-efficient and space-efficient. When solving this problem, there are a few common mistakes to be aware of. First, implementing a brute force approach incorrectly is a frequent error. If you generate all possible configurations of the M-balls without pruning invalid states early, you'll end up processing a huge number of unnecessary combinations. This drastically increases computation time, as the complexity can balloon to O, C, N, M, *validation _time. To address this, you should use smarter enumeration techniques, such as early exits during validation, to avoid redundant work. Another mistake is misinterpreting the problem constraints. For example, some assume that M will always be large or that the number of baskets is fixed. This can lead to either over-optimization for certain edge cases or failure to handle scenarios where M is very close to N. Always read the constraints carefully and test situations like M equals 1 or M equals N. Finally, off-by-one errors in binary search are a classic pitfall. If you don't update the low and high pointers correctly, you may end up with infinite loops or incorrect results. Binary search requires precise pointer updates to function properly, so make sure to clearly define your conditions and test with simple examples to ensure correctness. Another critical area to focus on is edge case testing. Skipping these tests can lead to runtime errors or incorrect results, especially for scenarios like having the minimum number of baskets, maximum spacing between baskets, or duplicate basket positions. To avoid these issues, explicitly test edge cases mentioned in the constraints, as well as any other corner cases you can think of. Additionally, overcomplicating the validation logic for binary search is a common mistake. Writing convoluted code to check if a given magnetic force is valid makes debugging significantly harder and increases the risk of introducing bugs. Instead, aim to break the validation process into smaller, reusable functions that are easier to test and maintain. This approach not only simplifies your code but also makes it more reliable under different test cases. Understanding the broader insights behind this problem can help you solve similar challenges more effectively. Many optimization problems that involve maximizing or minimizing a parameter while satisfying constraints often require binary search on the solution space. For this specific problem, the key insight is to recognize that maximizing the minimum magnetic force can be reframed as a decision problem, which is ideal for binary search. When explaining your approach, it's important to clearly communicate why binary search is a suitable method here and how you validate a given distance. Interviewers appreciate clarity and structured thinking. To manage your time well during an interview, you can start by explaining the brute force approach to establish the basic logic, then transition to binary search to demonstrate your ability to optimize. Finally, discussing edge cases such as M equals 1 / M equals N, or baskets that are tightly packed shows thoroughness and a deep understanding of problem scenarios. This problem also shares similarities with other LeetCode challenges that use binary search on the solution space. For example, in LeetCode 410, Split Array Largest Sum, you are tasked with a similar optimization problem. Likewise, LeetCode 875, Cocoa Eating Bananas, involves using binary search to determine the minimum feasible speed to meet a deadline. Another related problem is LeetCode 1011, Capacity to Ship Packages Within D Days, which focuses on minimizing the maximum weight capacity required to ship packages. Lastly, LeetCode 1482, Minimum Number of Days to Make M Bouquets, also applies binary search to determine the number of days needed to meet a specific constraint. Reviewing these problems can deepen your understanding of how binary search can be applied to a range of real-world scenarios. Finally, let's explore some alternative approaches and their trade-offs. A brute force solution is often the easiest to implement and can help you understand the problem better. However, it is computationally expensive and doesn't scale well for large inputs. Binary search on distance is the most efficient approach here, offering a time complexity of n*log max_distance. That said, it requires careful implementation of the validation logic to ensure correctness. Greedy algorithms may seem intuitive for certain variants of the problem, but they don't guarantee the optimal solution in this case. For optimal performance during interviews, focus on the binary search approach. Make sure your validation logic is robust and well-tested, as this will showcase both your problem-solving skills and your ability to write reliable code under constraints. Thank you for following along. In this session, we explored the magnetic force between two balls problem and applied binary search to solve it efficiently. Remember, optimization problems often benefit from a structured approach like binary search. Stay tuned for more solutions, and happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!